Did you all see the solutions on OneNote? We can go over it. The only thing I did is took the problem we did for homework, did on the board, and I reduced the complexity so it was very, I thought, solvable. If you want to, we can go over it, but I don't honestly think there's a need to because it's straightforward. Most of the people, now here's the one thing I gotta tell you. When I give you formulas on the board, and the only thing you do is apply them, I can't give you any partial credit. Do y'all follow me on this? I have no choice. There's only one thing you have to do. Just put it down and that's it. It wasn't meant to be hard. It was actually meant just to check if you've done your homework. And obviously there's some confusion about that stuff. So I'm gonna ask you to please stay up with this. And I warn you again, the worst thing to do is do a Thursday night cram session and come in expecting to do well on the quiz. Because during the lectures you think you got it, you got it. That's a dangerous thing in this class. Because it gets kind of tricky. Matter of fact, it gets very tricky. And I don't know, frankly, I looked at some of Adele Bashir's quizzes and tests. They're much harder than stuff I'm showing you, much more difficult. I don't plan on trying to make it complicated, but I do mean this. Please try to stay up with this stuff, because that's the key. There were a lot of 10s. I don't know how many, there were plenty, but there were a lot of very, very low grades where everything was wrong. They didn't have, I don't even think they understood what I put on the board with a factorial. That's not an exclamation mark. It means you multiply the numbers like it was n factorial. It's 1 times 2 times 3 times 4, all the way up to n. That's what it means. I mean, some people didn't, I don't think, knew that. So please be attentive with that. All right, now, if you want to, I'll go over it. But what I want to do is talk about a couple of things. And here's sort of my goal today. I want to go over the binomial distribution, the mean, standard deviation, and variance. I want to go through Poisson's distribution. If I have time, the hypergeometric, but really Poisson's is more about banking and finance, but it has applications to engineering too. And then go into the continuous variables, where we talk about continuous functions and the probability density, not the probability mass function. So let's see what I can do now. All right, so we're going to talk about the binomial distribution. We're going to do a couple of problems with this, but let me just put this down. Now this one, I'm going to expect you to know. Binomial is it's used everywhere. So when we talk about, and the way the book does it is a little different, but I'm going to put the way I've done it. When you take a look at the probability of taking k items where you have n total, n is greater than or equal to k. I'm just using this notation because it's the most common to me. That's n factorial over n minus k factorial, k factorial. Then it's going to be times p here, and that's the probability of a success to the k, times 1 minus p to the n minus k. Now, oftentimes they just use q as 1 minus p. You can only have two outcomes. Either it's a success or a failure with binomial. Everybody follow me on this? And again, there's a probability of success, p, and a probability of failure, which is q, 1 minus p. This is the standard stuff. Have you all seen this before in some of your classes? What class, do you remember?
I started a discrete math class.
Well, I mean, of the required courses. Have you seen it or not? Okay. A lot of times, and it depends who you get, I guess, in calculus or one of your courses over in mathematics, they'll explain this because it has a direct application to some of the stuff they're talking about. All right, so this is really the chances of getting k items, with a k having a success rate of p in n attempts. That's it. That's all it is. Now, if you take a look at this, the mean value or the expected value of this thing, and oftentimes in the book what he actually does is this. He won't have this, he'll have, I think it's called B or capital B, I, N, and then he'll have N, or I'm sorry, X, capital X equal X, just X. This is the same thing basically as K. And he'll have a semicolon, no, colon I think, and then he'll have of, I think it's xk, but it doesn't matter, it's a symbol. K comma n or n comma k. And that really he'll have then as that, which is going to be simply, now x is going to replace k, So you're gonna have n factorial over n minus x factorial, x factorial. He chooses to do it this way. P, and then it's going to be over p to the x, 1 minus p to the n minus x. And I don't know what page it's on, but here he's talking about, if we talk about the outcome of this being a random variable. Do y'all follow me? That's all he's saying. And did you all see this in the book, by the way? Do you know what page that's on?
I think it's page 99.
All right, page 99 in your text. Take a look at that. So now when we talk about the expected value of x, capital X, that's a random variable, being x, it's nice. It's just p, the probability of success, times n. That's all it is. And that should be in your book. Do you all see that? Look up binomial distribution, it would be standard deviation, variance, and mean. You can look it up in the back of the book. I think I wrote down the page numbers. Can you find it?
The mean and variance of the binomial variable. Page 101.
So this is on page 101. Now, I wish he had these blocked out and put in the back of the book for quick reference, because a lot of this stuff you're going to reference over and over again. This one you'll probably remember. So this is the expected value, or the mean. And for mean, a lot of times he uses mu as the mean. Y'all follow me? He just chooses to do it. It's fine. It's used by in other books. Now, when you talk about the variance of x, or the variance of this statistical function where x is like k, the variance is just going to be equal to p times n, and he'll put q in here, I think, and q is simply equal to 1 minus p. That's all it is. So the variance is n times p times q. And in a problem, I think it's problem 52 in chapter 2, I believe it's that, you can check. That's where we prove this. I'm not going to prove it right now, I'm just showing you that. And the way to do it is obviously, if this is the probability, right? If we have n outcomes, the thing is multiply this by k, because that k is going to be like the value you're looking for, right? That would be the expected value, and then you would have to sum them from really k equals 0 to n. And you would get, in fact, this value for the mean. And if you then had the mean, you subtracted x minus the mean squared times this probability, because that is a probability of something occurring. Then, and you summed them all up, then you would get this variance. And by the way, what's the standard deviation then for x? If that's the variance, this is really what? Sigma x squared. This is simply the square root of p and q. Does he have q in the book, by the way? Yeah. Okay, so that's all this is. Mean, standard deviation, variance for the binomial. With me? I'm going to mention this now to contrast it, because this is discrete counting methods. There's another thing in the book he talks about, and I'm going to jump to that. It's Poisson's distribution. Whenever I think about Poisson, what do you guys, have you had EMAG in here? When you hear of Poisson, just Poisson, what do you think of, anybody?
Fish.
Poison?
Poisson.
Is that fish?
Yeah, in French.
All right, well, you know what? I think you know this, but there's the Poisson equation. There's Laplace and Poisson. Poisson equation is what? Del squared to the potential V is equal to, what is it? Minus rho V over epsilon. Do y'all remember that class? That was a Laplacian operator. If it equaled 0, it would be Laplace's equation. If it's equal to the charge density over epsilon, it's equal to Poisson's. Does anybody remember this at all? The word Poisson. All right, if you have an EMAG book, you've got one. It's right back there at the back. I mean, it's in the book if you look it up, but that's not what he's talking about. By the way, a lot of these mathematicians and physicists like Gauss, Poisson, and I think about Fermat, they have tons of proof that have their names on them and formulas. Now, he uses P of X with U. I don't particularly care for symbols, but that's all right. So this is really going to be u to the x over x factorial times exp, and this is going to be simply to the minus u. Now, I'll get to what this means, but this Poisson's distribution is again something where you're going to remove components. You all follow me? Where it would be the probability of removing or of getting, and you have to talk about success and failures, They do a lot of stuff with green balls and blue balls and stuff like this, but here we're having a discrete output, you all follow me? And we have U here, which is the mean. So for the Poisson distribution, you get quite a bit of information about this. The expected value of this distribution of where X capital is X in this Poisson's distribution is just U, which is nice, so that's the average value. And strangely enough, the variance of X is also U. A lot of times I see it with lambda, and that means the standard deviation for this Poisson's distribution of X is just the square root of U. So average value and variance have the same thing. Now, in statistics, this is used all the time, in finance operations. Has anybody come across, did you have any kind of like engineering economics or anything like that? When you had it, did they show you the Poisson distribution? They didn't at all? Okay. We'll talk about why that's appropriate. And remember, this has nothing to do with that. This has, basically it has to do is, if you knew something had a certain type of statistical behavior, and I'm gonna have to read a little bit more about this before I present it, because I don't use this in electromagnetics. We use Gaussian distributions all the time and Rayleigh distributions, or I should say for radar. This stuff is basically built around finance, this one, and it models it well. But I thought I'd show you this. Now, I'm not gonna do the hypergeometric yet, but I did have some things I wanted to talk about with problems. And I'm trying to keep this simple. We could go through hypergeometric, gamma. There's many, many, many other distributions that have to do specifically with events like banking and finance, things where, a lot of discrete events where you have take and replace, where you have take, don't replace, all right, then take, replace, where all these conditions are put on the actual way you statistically grab stuff. And this is only for either a success or failure. By the way, in radar, for the stuff, we want to identify either the target's there or not there. There's a fundamental decision we make in a lot of the things that have either a successful or failure outcome based on other factors that influences. They fit binomial, to some extent at least. All right. All right, so if we go to example 2.34, do you mind doing that? Want to do this one? I'm going to get to my overheads though. I mean, those PowerPoints, hopefully it works, but here's what I'm really trying to do. I'm trying to get out of discrete stuff with all the stuff you need to know about discrete random variables. We've talked about conditional probability. We've talked about the expected value. We talked about the variance. We've talked about the mean. Now we're talking about different distributions where we can get all these things and how now some of these things are applied to problems. And if you have that example, this is 2.34. Can you give that to me?
If 75% of all purchases in the store are made with a credit card, X is the number among 10 randomly selected purchases made with that card.
All right, and X equals a random variable, did you say?
It's the number of yes, among the 10 randomly selected purchases. And then it says X, then 10, comma, 0.75.
Oh, I didn't. Yeah, and he does this. So he's gonna have this. For this problem, he's gonna have like, I think it's small b, is it BIN?
It's big B. It's big B.
It's big B. Big B, and then he's gonna have N, and then he's gonna have, does he use XK or XN?
It's
capital X, tilde, capital B, IN, and then in parentheses 10, comma, 0.75.
Here, I'm sorry. I do this a different way. Oh, he has 10 events with a probability of success being 0.75. That's what he's talking about. So really, he's not even bothering with some of the other notations. So he has, is it BIN or just B?
BIN.
Yeah. It's the binomial distribution, that's the only thing that's short for. He chose to do that. I think it's standard, but I'm not sure. And then he has of 10 with a success rate of 0.75. And what does he ask?
It goes on to say thus, E of X equals.
The expected value.
is-
So this is binomial. You all hear me on this, class? He just wants the expected value of this. Matter of fact, I'll tell you what, we'll just not even put that there. I want the expected value of X if it's a random variable and there's 10 occurrences. So I'm just gonna put down N equals 10. 10 occurrences, the probability of success is 0.75. You all follow me? Now this is the expected value. What did I do? This binomial. I put down somewhere, the expected value is just P times N, right? I'm trying to make sense of some of this stuff because the notation in his book is not what I'm familiar with in a standard way. This is what he chooses to do. So the expected value is just P times N, or the number. So we have a probability of 0.75 times 10, or this should be 7.5. And he has that right. The next part is what?
That's a variance.
All right, now this is just a direct application of it. That's the reason I chose this. It's in your books, it shows it. But he does use that BIN notation that I don't really care for. The next is he wants the variance, which is really variance of X is simply sigma of X squared. And that is what? That's simply N, right, times P times 1 minus P, or Q. So here we have 10 minus 0.75, and then it's times 0.25. I forgot what that is, but it's much smaller. It's a quarter of that, which is 1.875 according to the book, right? So that's the standard, or the variance. And what would the standard deviation be? It's as simple as it looks. And that's 1.137 or something? What is it?
1.37.
Yeah, so that's it in a nutshell, almost too simple, but you're gonna have to read his notations on that. And then I wanna do, and I did this one on MathCAD, and I may show you MathCAD. This is problem 2.52. And the reason I'm doing this, has anybody here used MathCAD? Has anybody used MATLAB? Everybody should have had exposure to MATLAB. It's considered part of the curricula, the thing you should need. Well, you can use MATLAB, but I'm gonna show you a trick with MathCAD, and it's so easy to do. And then, what is there's Mathematica? Has anybody used Mathematica here? You have?
Just,
All right, I'm telling you this is for the future. When some of you get out, and you're gonna have to write journal papers and things like this, or write formal articles for your managers, things like this, the two options usually are Word or LaTeX. Have you ever heard of, how many have heard of LaTeX? LaTeX is honestly the language that most people in mathematics, science, physics, and choose to use. Word is simpler in some senses, but LaTeX has more, it's more versatile, it's typesetting, it's perfect, and when you get to know it, you'll love it. Well, in LaTeX, if you use Mathematica to do anything, Mathematica, it will give you a general solution to an integration or a differential equation. Then you can, if you want the specific solution for given boundary conditions, it will do this for you. So just listen to me about this pitch, it'll help you. I wish I was told this when I was young. So with Mathematica, when they give you that general solution, they have an output of that in a LaTeX form. You can literally take that, cut it, and put it into your document. You don't have to, you know, if you work with LaTeX, you know, it gets a little cryptic with long mathematical formulas. There are, what you see is what you get, like math type things to do this. But for very long and complicated formulas, it's very hard. In Mathematica, it's a breeze, it's instant. You can get it, and then you can just cut it and put it into your article. Please remember this. As much as you love ChatGPT, you're gonna love this stuff much, much better, I promise you, in the long run. ChatGPT will not do this, not yet anyway. But I promise you this thing's a godsend. So I'm trying to tell you that. Just remember what I told you. I'll show you Mathematica in a second. First, I'm going to show that problem. Let me erase this and get this one up, because this one's actually, we're going to put the formulas up, then I'm going to show you how quick it is to do on MathCAD. I'm not going to use Mathematica here, even though I might, but you can download the free version. It does pretty much everything you need, except has this big thing that says, MathCAD lettering right down the middle until you get the FlexLM license from the server. And you can get this, I believe you can get this completely for free at the university. So if you go to problem 2.52, this is problem now. 2.52.
So when circuit boards used to manufacture DVD players are tested, the long run percentage of defectives is 5%.
All right, stop. He's saying the probability of a defect is 0.05, right? 5%. That's what we want. So he said, this is like a success, even though it's a defect. He's causing you to think. So it's 0.05. Go ahead.
Let X equal the number of defective boards in a random sample size of size n.
This is the random variable, and it's the number of defective boards, which are successes. He's making you think this. Go ahead.
Random sample size n equals 25.
So we have n equal 25. Go ahead.
So X tilde, then 25 comma 0.05.
All right, so he wants to know, and he has bin, right?
Correct.
Then he has x tilde, comma, I'll put n here. This is really gonna be the bin of x, right here, 25. And what that is gonna be the expected value. Y'all follow me on that? Now, this is a binomial distribution, right? The expected value, I erased it, is just what? The number of really items, right? N, it's the number of whatever you want to call it, trials, sometimes they use, and it's times the success rate. Y'all follow me on this? Just N times P. In this case, it's going to be 25 times 0.05, and what is that? Pardon me?
Did you want problem 52 or example?
Problem 52.
Okay.
Isn't that problem 52?
There is. I was looking at example 2.52, that's why I was confused.
We can do that too. But let's do this one first, okay? All right, y'all follow me in this class? So what is this gonna be at?
1.25.
All right, 1.25, and I'm gonna put down, this is simply the expected value of x. Now next, what does he ask for?
Determine probability of X less than or equal to 2.
All right, you hear that? We have 25 items, and we want the probability of x less than or equal to 2. Y'all hear me on this class? So what this amounts to is, and let me put this over here because this is the way I like this. For binomial, I like to write it as p of k comma n as just n factorial. You can write this, I'll show you some different ways to write this. Then it's going to be of n minus k factorial, success rate to k, 1 minus p, which is the failure rate or the non-success rate of n minus k. That's the one I like to use. He'll have it sometimes as this. He'll have it p of, I think it's x comma n, something to that, it's capital P, I think. And he'll have this as just n over, or sorry, nk. As such, he uses this notation. Do y'all follow me? He chooses to do that. That means this. So when you have nk here, it means n factorial, n minus k factorial times k factorial. That's all it signifies. Then he'll have that times p to the x, and sometimes he puts q to the n minus x. Here, q is just equal to 1 minus p, and that's the only thing he wants. So back up here, y'all follow me? I'm just I'm showing you his kind of notations in the book. I don't really like that BIN thing. I just put the expected value to be a lot easier, in my opinion. So now he asks for, what's the first part?
Probability that X is less than or equal to 2.
Or this is part B, right?
Part A.
That's part A? Okay. So probability of x, random variable x, less than or equal to 2. Now, if you look at this, this is binomial. Either it's a 1 or 0 kind of thing, binary, right? It's either defective or not defective. That's the only choices. So here, and I'm going to use this notation, it would be the probability of 0 defects in n tries, right? And n is 25 for this one, plus the probability of 1 try, or 1 defect in n tries, plus the probability of 2 defects in n tries, because he's looking for the number of defects, right? You all agree with that? What's another way of doing this? Well, you know, if you take a look at the probability of 0 defects, 1 defects, 2 defects, blah, 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 all the way 25 out of 25 defects, that's got to be 1, right? So you could take 1 minus the probability of 3, 4, 5, all the way up to 25, but it would be a lot more work. Y'all follow me, class? So that's the first. And I'm going to do this on MathCAD, but I just want you to see this. Y'all with me? What's the second part?
Probability of x
Or
greater
part
than,
B?
x greater than or equal to 5.
All right. How do you do that one, class? Remember, it's binomial. What would be the shortest way to do it?
You get the you get the 3, 4, 5.
You would take 1, right? That would be the probability of, I mean, that's basically the probability of 0, 1, 2, blah, 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 all the way to 25, correct? You would take that and you'd subtract all of them up to what? They want equal to or greater than 5, so it'd be 4. Do you agree with that, class? So here, you would say 1 minus, and then probability of 0, n, plus probability of 1n, plus probability of 2n, plus probability of 3n, plus probability of 4n, and that would be it. We'll do this in a second. Do y'all agree with that, everyone? What's the next part?
Probability that x is greater than or equal to 1 and less than or equal to 4.
All right, now it's got a limited thing, but it's the same kind of thing. It's counting the possibilities, okay? So now he wants the probability of x greater than or equal to 3, did you say, or 2?
1,
1, sorry. Less than or equal to
4.
4. Now what's that gonna be? Remember, the positive outcome is what? A defect. He's making you think in a way that's a little contrary. Y'all with me, class? So what's this gonna be? Equal to means it has to have 1, so it's probability of 1 comma n plus probability of 2 comma n plus probability of 3 comma n plus probability of 4 comma n. Y'all agree with that? We'll do it in a second. Now, I'm going to tell you this much. You can write simple functions on MATLAB or MathCAD or Mathematica that will do this in an instant. Matter of fact, I can modify my MathCAD stuff to accommodate almost any problem in the back of the, or in the back of chapter 2 quickly. All right. Is there another part?
What's the probability that none of the 25 boards?
All right. So how do we do that one? He wants the probability of none, or of x being a defect being 0, right? Right? None of the boards are defective. What's that? Remember, a defect is a positive outcome, or it's true, whatever you want to call it, right? So what does this actually give us? It's the probability of what? The number of defects out of n values, right? So this is just 0 of n would be 0 defects. Do you agree with that? You with me? So this one is just what? Now just look over here. This is one, you kind of got to pay attention. If k is 0, then we have n factorial over n factorial, correct? And 0 factorial is 1, correct, class? So we just have what? We have p, remember, p is 0.05, right? K is 0, that goes away, right? Here, it's going to be 1 minus p, or 0.95, right? If it's 0.05 of a defect, it's 0.95 to the 25th power. Do you agree with that? So this one is just 0.95 to the 25th power. Is there another part to this?
Yes. It wants you to calculate the expected value and standard deviation of x.
All right.
issue on.
What do you do for that one?
Uh,
Well, the standard or let's do the variance, right? Variance of x, the random variable, is just what? N times P times Q, 25 times 0.05 times 0.95. Do you agree with that? Whatever that is, the variance, what's the standard deviation? Square root of that, of the variance of x, correct? And then what else does he want?
Expected value.
That's me, the expected value of x. What's that gonna be?
NP.
Times n, right? All right, p is 0.05, n is 25. And we're gonna get all these in a second. Y'all follow me on this? This gets irritatingly boring because you see the natural progression. But if you don't do it several times, come quiz time, you'll fumble. Almost always. People fumble if they don't immerse themselves in these problems. And I bet you some of you are kicking yourself because the mistakes you made is that you didn't probably spend enough time doing problems just to have it burned in your head so you can't mess it up. I'm telling you, the probability is that way. All right, let me see if I can get this up. Now, we tried this last time, it didn't go so well. And then I may talk a little bit about MathCAD only because, MATLAB is because you're supposed to know it, but I've learned this lesson the hard way. When I think people know it because I'm told they've had it, they don't know it a lot of times. MATLAB isn't hard, but you have to keep up with it. All right, so this is MathCAD. Now, you see that MathCAD Express, isn't that on?
Yeah.
All right. You see this line right here that says MathCAD Express? Yeah, I know. Here's what I have to do. I have to go to Global Protect. And you'll have to do the same thing. You use that, right? The VPN Global Protect? You have to do this. I don't know why. I do know why. And now, that should go away in a second, I think. Then I have to do this. You won't have to do it if you start with Global Protect on. But the nice thing is this is free. And you can get that license over there at Engineering Network Service will provide you what I've got here, I believe. And now it should go away. Yeah. All right, so it's gone. This thing is just nice. I like it. So here's the function form that I have. I have, if P is going to be the probability of a success, in other words, the outcome I want, regardless if it's a defect or not. And N is the number of trials, total number, and K will be the number of, quote, successes out of N trials. You all follow me in this class? If we do this, so I make a function. I said if I want anything cumulative, like the probability of 0, 1, 2, 3, 4, and so forth, successes, I just made this. I just sum up all this from K equals 0 to A. It's easy to do. There's my function, all right? Now, MATLAB, you can do this, but you have to rerun this continually every time you alter anything. So the first part A, what was part A again? Probability of a defect in 0, 1, and 2, is that right? All right, so and I have the probability is 0.05 and N is 25. So I just simply look at this right here, this, and add them up, P of 2, and that's it. It's 0.873. Is there an answer in that? Did I give you that answer or not? In chapter 2, did I put the two answers up or not?
No.
I thought I did. Can somebody send me an email to put chapter 2's answers up? I thought I did. It's not on now?
No.
I didn't see it last night.
Send me a message. I put them up. I gotta be careful about this, but I'll put them up for you. You all with me? Because I'm teaching this in class, I can reference solutions. Okay, is 0.873. The next part B is the probability that it's great, there's more than 4 defects, right? Probability of 4 or more, right? Or is it
Greater than 5.
5 or more. So it's 1 minus the probability of 4. And by the way, these answers are right, I checked. Y'all with me, class? But you see, this is trivia. Now, in your calculators, I want to tell you this. I believe your calculators have this in it functioning. The binomial distribution, the cumulative distribution binomial.
I didn't want to tell you, but yes, they
You can tell me. Oh, which calculator?
do. The TI Inspire.
All right, he says the TI Inspire does. This is going to save you time. Now, there may be some things you have to tweak, but it's nice to have this available. What's part B? I mean, part C?
Between 1 and 4.
All right, so here's what I do. They want it between 1 and 4. So I take the probability all the way from 0, 1, 2, 3, and 4, which is this cumulative one, PT of 4. Can you all see this, by the way? Let me move that up a little. All right. It's this. It's PT of 4, which is the sum of all up to 4, minus PT of 0, so you get rid of 0, right? Because it's 1 to 4. Y'all follow me? And again, check and see if your calculators do that. Is that, what's the name of the function in yours?
Yeah, if you go to like the menu on the TI Inspire, there's a probability, and then it'll give you distributions, and then it's like at the very bottom, binomial PDF.
Do they have Poissons?
Yeah, they
And do they have hypergeometric?
do.
We're gonna do Poissons and hypergeometric, and that's it. I'm not doing gamma and all the other ones. Do they have Poissons at least?
They have Poisson and geometric.
Hypergeometric?
It doesn't say hyper.
It is.
Yeah.
We'll talk about those, not right now, but we will talk about and where they're applied. I just wanna make sure, how many have, how many have Inspire? How many have TI 89? One? I think they have that. How many have, what do you have?
HP.
You got an HP?
Yeah.
That's what I use. That'll have it, I'm almost guaranteed. What model?
50G.
See, the HPs I had in 1989 will do, I mean, actually, even earlier, but in 1994 about one, 1989, they do everything that I need. Everything, matrix math, all that. The TIs are more focused at, I'd say, an application directly to classroom use for most classes now, not just engineering. So you have to get like the 84, 83, 84, and 89, and 93, I think, to get functional stuff for engineering. Anyway, what's the next one? P of 0, right? That's just, if you want the probability to count from 0 to 0, it's just probability of 0, which is that. You can try that on yours, see if you get that value. This is binomial. You get it? How many tried that and get it? If you got it. You're doing it now? Or did you do it later?
I did it earlier.
Okay.
Put it on my- I don't have a button for
What's that?
it. I don't have a button for it on my calculator.
Okay. If you get used to this, it'll help you, promise you. So then finally, this is the last part, E, right? And that's just the probability of no defects, right? That's probability of 0, right? Which is just, I'm sorry, the expected value. The expected value. That's the number of trials times the probability of what we call a success or a defect. And that's it. The standard deviation is again just P times N times 1 minus P, or Q would be the variance. The square root of that is 1.09. Can you all follow me? Now here's why I like that. Suppose, you know, and I don't know how easy yours are, but if you wanted to change it, suppose the next problem says instead of 25, they have 30, or say they have, 30, instead of a probability of a defect is 0.05, suppose that it's 0.008, and this is make it 35, all right? Now watch. Instant. Y'all see this? What you see is what you get without any alterations. Now, why is that so important? Most of these problems have the same exact formulas. The only thing that changes may be the number of, if it's binomial related, the number of trials and the probability of success or failure. That's it. And they'll have all the same forms. Probability from 1 to 10 successes, whatever they are. They'll have probability of maybe 1 success and 2 success and 5 success. You all follow me? So you can do this quickly. That's what I'm getting at. Now, MATLAB will do this, but it's a little more cryptic. you have to create something, a script, they call it MATLAB, and I rerun it over and over, and I have to modify it. Now, you can make a MATLAB function that'll have all the possible things that can change and just call that, but you still have to run it. Y'all follow me? So this is easier. I'm saying this because I can do these problems in literally under a minute, almost all of them on here. It takes me a while on MathCAD, or MATLAB, or on Octave is the free version of MATLAB, I think, in my mind. And so I'm just telling you, this is what I use. And there's professors, several professors that use this because it's so quick and easy. All right. I don't own the company stock. This is nothing I'm going to get anything back from. I'm just throwing this out there. And this is version 9. It's called MathCAD Prime 9.0. You can download the thing. It'll have most of the functionality. You won't be able to get you can't get the argument of a complex number easily, but all that stuff you don't really need. Y'all follow me? If you get a chance to try it, I don't think you'll regret it. All right, that's that. Now, I got more problems I'm going to do here, but I figure out why I'm here. I might as well go ahead and take care of these slides that I want to talk about. So this is a thing that didn't come up before, and I'm going to go through this kind of quick because we've covered most of this. All right. Now, we talked about for continuous time the probability density function. You'll see this stuff, the probability mass function that he has, where he just talks about the probability for discrete values, is basically the same thing as the continuous probability density function that we use in chapter 3 and 4 onward, all right? And we'll use this a lot more than we will discrete stuff. So the first probability is, well, this can never be negative. This is the probability density function, f of x. You all follow me in that? It can never be negative. You can't have a negative chance of something happening, or else it doesn't exist. The next is the probability of the event occurring over all possible ranges that it exists in has to be 1. And again, these are where 1 would be like 100% chance. The next is there's something called the cumulative probability, or he calls it the cumulative distribution function in your book. The only thing it means is if we integrate from the beginnings, the negative beginning value possible, and whatever it is, to the value of x, what's the probability of that value being within that range? Now, y'all follow me? It's just the integration of the PDF. We'll do some problems on this, and that's all it is. And I mentioned this to you, and it should be obvious. Y'all with me on this? And by the way, what happens when x is infinity here? Right in that argument. Class? 1. It's got to be 1, right? That means you went from minus infinity to plus infinity. Now, if you look at this, just for a second, I know I hate PowerPoints. I think they'll be beneficial here. If you just look at that, and you think about the last example, remember how if we wanted the probability of, I think it was x being greater than 5 or equal to 5, right? We simply took 1 minus the probability of 0, 1, 2, 3, and 4, correct? All right. Now here, if you want the probability that x is greater than a value, well, you can take 1 minus the probability, or this cumulative probability function, where you put x equals that value. That should make sense to you. Y'all follow me on this? I'm just showing you this, because we're going to see we have 2 different functions coming up when we deal with Gaussian stuff, and one is simply 1 minus the other function, and just keep that in the back of your mind. Finally, the probability of the value of x being anything, any random variable between x1 and x2 is just the integration of the probability density function over that range. Y'all follow me, class? Simple and straightforward. How many look at these things right here? The slides I put up, 1, 2. I'm going to show you, until you apply them, you don't really appreciate them. And I cannot overstate this. If you want to be successful in this class, do lots of problems on a daily basis. Don't wait till Thursday night. The only thing I try to tell you this, talk to, who's had me before in here? Anybody? All right. Is that ring true to you guys or not? I hope to go, I think most of the guys here, as far as I know, you guys did pretty good, but I don't know. the grades are done automatically, so I don't know. I mean, I just put in things and I'm done. But that is the godsend for you, and I promise you, what I'm telling you is the truth. I've had you one time, but you had a problem, so, but I remember this. So here we have, this is a density function. Now, one of the things you have to be sure about, if you want the value of k, you have to integrate this density function over the range that exists. You see that u of x? That's the what? Unit step. It start at u of x equals 0. It turns on. It goes from 0 to 1, right? But u of minus 1 would be 0. So the density function itself only is good for 0 to infinity, correct? So if we wanted this value k, the only thing we'd have to do is integrate this density function and set it equal to 1. You'll notice the integral from minus infinity actually starts at 0 because below that, the functional form is 0. Can everybody see this, class? I'm not trying to fly, but I'm trying to just give you the essence of it quickly. So that means when you integrate this from 0 to infinity, you get this, then you evaluate, you get k over 2. It's got to be equal to 1 or k is 2. That's how you get any unknown constants if you're giving the form, the mathematical form of a density function. Have you had this before by any chance, any of you? I'm not sure. If you've had it, it had to be in your math classes, I think. You didn't have it? Okay. Next, what's the probability of x being great? It should be greater than or equal to 1 because at 1, it's undefined. So here we would integrate the density function from 1 to infinity and we get this value. Now the next part, just remember, I'm saying this only because people mess this up. The probability of x being less than a half would be really 1 minus the probability of x being greater than a half. Do you agree with that? So the way he's going to do it, for x less than a half, he's just going to go from 0 to a half and get it this way. And you can see that that's 0.632. But we could just as well take 1 minus the functional form from x being greater than a half. You all follow me? And you would integrate from a half to infinity and subtract it from 1. Making sense to everybody? It seems boringly simple until you get problems that are a little tricky, and then it gets complicated in a hurry. So next, this is tricky. They say there's going to be a function y that is equal to x squared. Now here's where it gets tricky. X can have positive values only, right? And don't think back to the prior density function. Here he's going to say a random function is going to be y is x squared. Please think about that. Y cannot be negative. You all follow me? But x can be negative. You all with me on this? Because it's not the prior function. If it was, it'd be easy. So if we look at, has anybody looked at this one? This is a great problem because it really showcases one of the things people stumble on. So if y is equal to 6x plus 3, and we want the probability of y being less than a certain value. With me on this? That's the probability of 6x plus 3 being less than that value or equal to that value. You all follow me on this? So that's the probability of x less than or equal to y minus 3 over 6. Do you all see how he's just shuffling these things? Y is going to be something that the small y is given. We would have like y would be 1, 2, 3, 4. You all follow me in this class? It would be a known, and now we're finding out what this is. So it's the probability of y minus 3 over 6, and you could break it down as y over 6 minus 1/2 if you wanted, but it's in essence the same. So it's the probability of y minus 3 over 6. This would be really what we're talking about. Now here's where it gets tricky. Just for a second, think about this. If y here is 6x plus 3, we're not doing the one where he has x or y squared yet. Then if you take a look at this, the derivative of f of y, capital F of y, the cumulative function with respect to y has to be, now I didn't put that there, but you realize that if you have something that's the integration of like f of x dx from some point, say minus infinity to x, and it should be the integral of f of x prime. If you just think about this, if you know that capital F of x is really the integral from minus infinity to x of some f of x of, say, u du. I put u in there because it has to be a variable that isn't x. You can't integrate, at least mathematically, with the same kernel of integration variable as a terminal value. Do you all follow me on that, class? So I'm just using u there. Well, when you take a derivative of f of x with respect to x, what do you get? Well, the fundamental theorems in calculus say what? You're just evaluating this at x, right? We could actually write the form down. Do you all follow me on that? It just is f of x evaluated at x. That's all it is. You all with me? So by the same thoughts, if we take a derivative of f of y dy, we're going to get fy of y. And just bear with me on that. There's nothing tricky here. And there's no subtle, there's nothing hidden. It's very obvious. So if you come down here, he says, well, f of y is really f of x, that's up here, from y minus 3 to x, or to 6. Y minus 3 over 6. Correct, class? Let me move this up. I can't do it. I hope you can see this. I know some in the back may have a hard time, but I can't do anything with that. So if you look at this, we take the derivative, we actually have to go from minus, you'll notice for x, when we have this, I'm sorry, I missed this one. So here, this, when we take a derivative of f of x, right here, of y minus 3 over 6, because that is f of y effectively right here, then you're going to get the derivative, derivative with respect to y of f of x. So it's really going to be this functional form evaluated with y minus 3 over 6. So when I take a derivative of that, now take a look at this. The derivative of this brings a 1/6 out here, pardon me, because it's going to have x. Y is going to be, x will have 1/6 out here, and then it's going to be f of x of y minus 3, or it's 1/3 of e to the y minus 3 over 6 u of y minus 3, and it's shown here. I'm going to show you a few other things about this in the coming classes, but does this make sense right here, what I'm underlining? And does this make sense? Right here. Now, this capital F of x just means the integration of this function from 0, or from minus infinity, or wherever it starts, up to the value y minus 3 over 6. You follow me, class? Now, when I've got that, that is this, f of y. You follow me? Take that, or take literally this, and stick it in here, and take a derivative. So if you take this, y minus 3 over 6, and put it in for x, you get y minus 3 over 6 here, but that's really just y minus 3 for u of x, isn't it? If you have y minus 3 over anything, the only thing you care about if it's greater than or less than 0. Follow me? So that's how come down here you only have y minus 3. Then when you take this, you have to put in 2e to the minus 2, and then it's going to be, instead of x here, it's going to be y minus 3 over 6. And when we take a derivative of that, it's shown here, you're just going to get the derivative of this function where x is replaced by y minus 3, get the derivative of that, which is going to have the 1/6. And let's see, after you fuss with that, you're going to get this. I'll go through that more in detail in a second. How many understand what I'm showing you here? Follow me on this? Now this is the one I want to talk about just for a second. This is one where we have a density function that has y equals x squared. And you're given the probability density function for x. So they're just showing you this is f of x. Now, when you look at this, if you talk about the cumulative density function of y, and here it's going to be y less than or equal to y here. If you think about this, for x negative or positive, y has a positive value Can you all follow me on that? So really, when you talk about the probability of y less than or equal to small y here, it's the probability of x less than the positive value of, it would be y squared, and greater than the negative value of y squared. Does that make sense to everybody, class? You have to account for the negative. And when you do it, here he shows you that this really is the density function we have here. He's showing you a Gaussian f of x, but it's integrated from the square root of minus y to plus y because y squared is equal to x. I'm sorry, x squared is equal to y, and therefore x for negative or positive values has a positive y outcome. That's the reason he's showing you that. So here, when you do this, there's my f of x from there to there. I have to take a derivative of this with respect to y. Now this is a different theorem in calculus. It's Leibniz's rule. And here you have to take the derivative with respect to y of this integration. You can put this in, but it's going to be this value, f of x evaluated at square root of y, and f of x evaluated minus the square root of y. And then you get the factor when you take the derivative of this of 2 over the square root of y. I'm going to have to go through this in a little more detail with you. All right, I'm going to give you some homework related to that, but I did want to mention one thing about this. For this problem, let's do this problem, and I want to do it over there for 1 second. I know I'm getting low on time. I'll spend more time on this next class, a lot more. You're going to ask me about a quiz on Friday? Because we got a short week, I won't give one this Friday. All right. I may give one midweek next week, but so for this problem right here, when you have capital Y is equal to 6x plus 3. And then they say they want the density function for py, capital Y less than or equal to small y. That's the same thing as the probability right here of 6x plus 3 less than or equal to y. And then he's just going ahead and he's modifying it to get this. So this becomes his f of y right here. And when he does the derivative of it, just take a straight old derivative. This is what you're going to get. That's it in a nutshell. Y'all follow me? He's defined this. This is the event. That's the cumulative distribution function. But y is defined in terms of x. So I come down here and I have this. Means this is an f of x. It's the cumulative distribution and function of x, which is over there. So then when I replace y with x, and I take a derivative, I get that, and that is the density function. The one thing that's important to note is now it's only evaluated from y greater than or equal to 3. You just try that one, and you'll probably see it. For the one with x squared, and he shows that density function, when he has, for the second part, you can turn the lights on if you want. Here he has y equals x squared, and he has some f of x. It doesn't matter what f of x is. He chooses one that looks like a Gaussian distribution right here. But it doesn't really matter. He's just showing you the possible values. X can have all values for this one. So if we take a look at the probability, or the cumulative probability, of f of like y being less than or equal to some small y, what we're really saying is that's really f, this would be f of 1, f of x of, and this would be of, and x would be the square root of y right here, or I should say of x, trying to do this, I hope you can appreciate this. It would be the same thing as x being less than or equal to the square root of y. All right. And it has to be this way. And it has to be at the same time, or and x being greater than or equal to the negative square root of y. I hope you can see what I'm doing here. Y'all follow me? Because x can have a negative value, will render a positive value for y, right? So what is this going to be? It's really going to be what? The f of x here would be equal to the integral from square root of y, minus square root of y to square root of y of f of x, whatever this is, f of x dx, and that would be this, right? Y'all follow me? I'm just saying now that's a cumulative probability. So if you want to get the actual value, this becomes f of y here, because the integration is terminated as a function of y. Then when you take the derivative of f of y with respect to y, this is a weird one. Here you got to use Leibowitz's rule, or Leibowitz's rule. Now you have to evaluate this here, plus you have to evaluate that here, and you're going to have to take a derivative of this function right here with respect to y, and do what it shows you from the next page. And I'm about out of time. I think I'm over. I'm just trying to show you this. We'll do that in more detail next time. And I'm going to give you some problems. Some of these may not be out of the book, but I do want to tell you, please do these problems. We'll talk about them. Where I'm headed with this is we're going to do problems that have to do with the mean, expected value, and variance for probabilities, general form, and then Gaussian. And then from Gaussian, we're going to Rayleigh. So I'll give you reading and some homework and stuff. Please come Friday. I'm not trying to do this in a way that's just cherry picking. I'm trying to develop something where everything I'm doing has to be covered, but I'm trying to show you the parallels between discrete and continuous. And I don't want to overburden you with a whole lot of functional stuff that you're never going to use. Hypergeometric you might use, but gamma and all that, unless you're a physicist doing radiation decay and stuff, you're not going to use it. Okay, thank you. Sorry I went a little over.